Well, during the last few years, I worked on Hevelius' theory of lunar liberation, and my paper about this will be published soon. So I decided to say something during this conference about, well, to give you a kind of prequel to Hevelius' theory of lunar liberation. So let's start. It is well known that the first complete description of lunar liberation was possible owing to observations of the lunar surface conducted by Johannes Hevelius. From November 1643 until April 1645, he systematically observed the lunar surface with a telescope. His efforts led to the extensive work entitled Selenographia, which was published in 1647. The Selenographia contains 3 large maps of the lunar disk, and this is okay, it works. Each of these maps covers the entire section of the lunar surface that is visible from the Earth. Therefore, these are the first complete renditions of the regions close to the edge of the lunar disk that periodically appear and disappear due to a joint effect of the principal types of lunar liberation. Later, the detailed studies of this phenomenon Hevelius described in 1654 in the treatise De Motu Lunae Liberatorio. However, the liberation of lunar apparent disk was known earlier, and in this paper I will survey all known sources and important works which dealt with the liberation of the moon before the publication of Hevelius' works. However, before I will refer to historical sources, let me to describe briefly essential elements of lunar liberation. In first order approximation, the moon rotates uniformly in the course of the month, at the same time revolving in her orbit around the Earth with variable angular velocity according to Kepler's second law. Although the periods of both motions are synchronized, changes in orbital speed cause an observer on Earth to see either the western or the eastern edge of the lunar disk, depending on the conditions. Because of this, the maximum angular shift of surface object relative to the center of the moon is plus minus 7.9 degrees. This is what we call optical liberation in longitude. And moreover, the moon's rotational axis is not perpendicular to the orbital plane, but tilted away from the normal to the orbital plane by 6 degrees 41 minutes, which is the reason why in the course of the month we have alternating views of the north and of the south pole of the moon. This phenomenon, known as optical liberation in latitude, leads to the angular shift of surface objects in relation to the center of the moon. One also needs to consider the observations of the moon's surface are not conducted from the center of the Earth, but from its surface, which each day makes 1 revolution around the Earth's axis. In this way, analogous to the phenomenon of diurnal parallax, we have diurnal liberation, also called parallactic liberation. Its maximum value is equal to 57 minutes. The 3 types of liberation described here enabled us to view not half, but 59% of the moon's surface. For obvious reasons, the period of liberation in longitude is the anomalistic month, the time between successive passages of the moon through perigee, while in latitude it is the draconic month, the time between successive passages of the moon through her ascending node. Due to the incongruence of these periods, the manifestations of liberation change from month to month. Optical liberation in longitude and in latitude can be illustrated as the oscillations of a point on the surface of the moon that marks the center of the lunar disk in relation to a line connecting the Earth and the moon at their centers of mass. In this figure, 2 diagrams based on this model are used to illustrate the variability of optical liberation by showing different paths of the center of the lunar disk for January 1635 and January 1643. Finally, we need to recognize that optical liberation in latitude and longitude has a direct consequence for an observer on the Earth, the changing position of lunar spots relative to the edges of the lunar disk. However, to notice this, we need a realistic drawing of the moon. And here the history of observations of lunar libration before Hevelius starts. It seems that the earliest naturalistic drawings of the lunar phase appear in the crucifixion painted by the Netherlandish master Jan van Eyck. A detailed view of the moon, shown in a gibbous phase, proves that the major lunar maria are all evident on her disk. A worthy successor of Van Eyck in lunar studies was Leonardo da Vinci. The journals of Leonardo contain well-preserved drawings of the lunar disk, originating from 1505 to 08 and 1513 to 1514, with the dark spots portrayed fairly accurately. Also preserved are Leonardo's notes, in which he mentions that careful observations of the dark spots on the moon reveal that the spots undergo changes. It appears, however, that this remark does not refer to the phenomenon of libration, but rather to the effects associated with the variable illumination of the moon, since in another passage, Leonardo states, quote, "The spots of the moon, as they are seen at full moon, never vary in the course of its motion over our hemisphere." In his recently published article, Stephen Pumphrey showed that probably William Gilbert was the first to notice the optical libration of the moon. Physician to Queen Elizabeth I and author of the famous De Magnete did it with the naked eye when he drew in about 1600 his map of the moon. Gilbert recorded that observation of the full moon in Capricorn shows that the distance of the moon's southern spot from the outer edge of shining light of the orb is greater than when the moon is in Cancer. This observation was not accidental. Gilbert wanted to know whether the lunar body, quote, absolutely does not revolve, or whether to some extent it does turn itself, and, another quote, how it inclines in its monthly motion with its poles towards some fixed parts of the heavens. However, his map and his deliberations on changes on the lunar surface were hidden in Gilbert's posthumously compiled manuscript work, De Mundo Nostro Sublunari Philosophia Nova, and its printed edition did not appear until 1651. So there is no sign that Gilbert's discovery made any impact on 17th century selenographers, except Thomas Heriot. Stephen Pumphrey found evidence that Heriot saw Gilbert's map in the original manuscript. This may be the reason why Heriot became the author of the first known telescopic sketch of the moon. And in the course of one of the 3 lunar observations he made in December 1611, the English mathematician noticed that 2 features of the moon's surface, today called Mare Frigoris and Sinus Roris, appeared closer to the edge of the lunar disk than was the case on the map he had drawn some time earlier. Since he did not follow up on this note, we cannot rule out the possibility that he thought his own map to be inaccurate in this respect. Nonetheless, we could consider this to be the qualitative record of libration in latitude. However, the handwritten notes left by Heriot were not discovered until the end of the 18th century, so most often it is Michael Florentius van Langren and Galileo Galilei who are given credits for first mentioning lunar libration. The Dutchman van Langren, royal cosmographer and mathematician to King Philip IV of Spain, wanted to create a map of the moon that could be used to determine terrestrial longitude through the comparison of sunset and sunrise times at defined points corresponding to the surface features of the moon. Planning this undertaking during a stay in Madrid in the years 1631 to 34, van Langren also intended to publish a theory of libration and instructions pertaining to how it should be applied when using the map of the moon. This information he put in the text of the legend at the bottom of his map of the moon, which was charted out in March and published in May of 1645 in Brussels. Therefore, he had to have already been aware of the phenomenon of libration at the time, although we do not know to what extent since the information contained in the legend is limited to one sentence stating that the spots on the face of the moon seem to be shifting either eastward, westward, or northward, southward. Van Langren was not able to carry out any of the undertakings related to libration that he had planned. At the same time, modern analysis of the map of the moon from 1645 show that although the mean locations of the craters illustrating on the map are not affected by errors in selenographic longitude, they do exhibit a systematic error in latitude. One can suppose that Van Langren took no steps to eliminate the effects of libration, while the accuracy in longitude is most likely the effect of his natural choice to use the terminator as the line of reference. Interestingly, the works of Claude Mellan also point to the fact that libration in latitude accounted for the significant errors on the early maps and drawings of the surface of the moon. This French artist, having had conducted selenographic observations under the eye of Pierre Gassendi and Nicolas de Peyresque, presented a map of the full moon early in 1637. As UN Whittaker observed, the map had to have been produced on the basis of two different maps of the waxing and of the waning moon, since the left part of the map clearly corresponds to a different libration in latitude than the right. In 1632, at the time when Van Langren was fruitlessly trying to obtain funding from his selenographic project from the Spanish crown, Galileo's dialogue concerning the two chief world systems was published in Florence. The Italian scholar earned his place in the history of lunar exploration owing to Sidereus Nuncius, which contains the first prints of the surface of the moon ever to be published, based on observations through a telescope. However, the phenomenon of libration is not mentioned by Galileo prior to the completion of the dialogue. Because the manuscript of this work was completed in January of 1630, this date can be taken to signify Galileo's description of certain aspects of lunar libration. On the first day of the dialogue, the character Salviati introduces, quote, a specific event newly observed on the moon by our academic. It clearly follows from this fragment what the author of the treatise is aware of, that from the Earth we are able to see over half of the surface of its satellite. He even provides a description of the observed phenomena. For there are two special markings on the moon, one of which is seen to the northwest when the moon is on the meridian, and the other almost diametrically opposite. The former is visible even without a telescope, but not the latter. The one toward the northwest is a small oval spot separated from three larger ones. The opposite one is smaller and likewise stands apart from larger marks in a sufficiently clear field. In both of these, the variation mentioned already is quite clearly observed. They are seen opposite to one another, now close to the edge of the lunar disk and now farther away. The difference is such that the distance between the northwesterly spot and the edge of the lunar disk is at one time more than twice what is at another. And to the spot being much closer to the edge of the disk, the change is more than threefold from one time to the other. The behavior of the two dark regions lying on opposite sides of the lunar disk is, of course, the combined effect of optical libration, mainly in longitude and latitude. In explaining this phenomenon, Galileo points to two factors. Paradoxically, he correctly identifies the first, but less important factor, diurnal libration. He relates the second factor to the inclination of lunar orbit in relation to the ecliptic. A similar from Galileo, a similar variation should be observable also at the northern and southern extremities of the same disk, according as the moon is at its most southerly or most northerly point along the meridian. When it is northerly, some of its northern parts are hidden and the southern revealed, and vice versa. The ambiguous nature of this fragment causes some to assume that in it Galileo presents the geometry of the phenomenon of libration in latitude, Koppel and Carder, while others only give him credit for his correct identification of diurnal libration, Regini. This lack of consensus originates from the fact that in order for libration in latitude to happen, the moon's rotational axis needs to be tilted away from the normal to the moon's orbit and needs to remain in a fixed position relative to the stars. Galileo, meanwhile, does not state this explicitly. It is worth noting, however, that in the dialogue, the remarks described here are immediately preceded by a short discussion of the possible rotation of the moon on her axis. In rejecting the idea of the lunar epicycle, and by so doing the moon's rotation on her axis, which is necessary in order for the moon to face the Earth at all times with the same hemisphere, Galileo states, quote, "The moon makes no revolution of its own." Yet, what is it that he is trying to convey here? The answer is to be found upon the day 3 of the dialogue in an extensive debate concerning sunspots. Ending the dialogue, Galileo recalls once more the phenomena, the existence of which he considers as the main argument for the Earth's rotation around the Sun. In addition to the retrograde loops of planets and the ebbing and flowing of ocean tides, he includes the yearly cycle of changes in the orientation and in the shape of the path of motion of sunspots across the solar disk. The starting point for developing the third argument is to define the most important features of sunspot behavior throughout the year. Only 2 times a year do they travel across the solar disk in a straight line. The rest of the year, when they travel in an arc, is divided into 6 months when the arc is turned upwards and another 6 when it is turned downwards. The year is also divided into 6 months when the sunspots, which appear on the left edge of the solar disk and disappear on the right edge, appear in a low position and disappear in a high position, and another 6 months when they appear in a high position and disappear in a low position. Subsequently, Galileo states what modifications need to be made to the Copernican and Ptolemaic system in order for them to be able to account for the phenomenon of sunspots. His reasoning is subtle, and a well-structured explanation of all the nuances it is based on would be rather lengthy. Here, the exposition will be limited to those elements of Galileo's discussion that shed new lights on his reflections about how, in total, over half of the moon's surface is turned towards the Earth. It was Galileo's goal to prove that after the modification of the 2 systems, the Earth's movement, according to heliocentric model, can be explained by 2 types of motion as opposed to 3, and that these 2 types of motions are simpler than previously thought. In the original Copernican system, 3 types of motion were assigned to the Earth: annual orbital motion, diurnal rotation on an axis of its own, and the annual precessional motion of this axis around the poles of the ecliptic. In the Copernican system, it is the precessional motion that is responsible for the Earth's axis maintaining a fixed position relative to the stars. To this model, Galileo added the rotation of the Sun with a period of about 27 days on an axis that is fixed in relation to the stars and inclined at a certain angle towards the normal to the plane of the ecliptic. Unlike Copernicus, however, Galileo assumed that the fixed position of the rotational axis relative to the stars is not the effect of its motion, but of its lack of motion relative to the stars. By this assumption, he could also eliminate the precessional movement of the Earth from his model and use the model to explain the behavior of sunspots within the heliocentric system. While describing this problem, Galileo imagined an experiment being conducted in which someone rotates a container filled with water with a ball floating at its center. His conclusion was as follows. We are proving that the third motion attributed to the Earth by Copernicus was not a movement at all, but a state of rest and immutable keeping of definite parts pointed toward the same definite points in the universe. That is, a perpetual maintenance of the axis of diurnal rotation, parallel to itself and pointing at certain fixed stars. This perfectly constant position, we were saying, belongs naturally to every body which is balanced and suspended in a fluid and yielding medium. For, though turned around, it does not change direction with respect to external things, but merely seems to turn upon itself with respect to the person carrying it, and to the ball in which it is carried. This generalization sheds new light on the meaning of Galileo's comment directly preceding the description of libration about the moon which does not turn on her axis. There is reason to believe that Galileo was only referring to the lack of rotational movement of the moons relative to the Earth. However, as in the case of any suspended body, he does assume that the moon's axis also remains fixed in relation to the stars. What is more, Galileo realizes that in wanting to explain the cyclic curving of the path taken by sunspots across the solar disk, he has to assume that the sun's axis is tilted to the ecliptic and that its position is in relation to the stars is unchanging, as in the case of the Earth. From this, we can assume that the fragment of the dialogue quoted above, linking the tilt of the lunar orbit relative to the ecliptic with the idea that over half of the moon's surface is visible to us, is after all a description of libration in latitude. Interestingly, we find subtle indications of such a reading of this fragment in the work of the French polymath and supporter of the heliocentric theory, Ismaël Bouillot. In the work Astronomica Philolaica, published in 1645, Bouillot shows that if the rotational axis of the moon were unchanging in its relation to the rotational axis of the Earth, parallel or tilted at a fixed angle, this would mean that the moon does turn on her axis, because in the absence of the lunar rotation, the moon's orbiting around the Earth would cause us to be able to see both sides of the moon. Because the introduction of another type of motion, the rotation of the moon on her axis, did not fit in with the philosophical approach Bouillot had taken, coincident with Galileo's approach that movements in nature are limited to the necessary minimum, the Frenchman paradoxically rejected the idea of the rotational axis of the moon being fixedly positioned in relation to that of the Earth as a possible explanation of the phenomenon of libration. Galileo's view on lunar libration are summarized in a letter written by him to Fulgencio Micanzi on November 1637. I have discovered a very marvelous observation in the face of the moon, in which body, though it has been looked at infinitely many times, I do not find that any change was ever noticed, but the same face was always seen the same to our eyes. This I find not to be true. Rather, it changes its aspects with all three possible variations, making for us those changes that are made by one who shows to our eyes his full face, head on, so to speak, and then goes changing this in all possible ways, that is, turning now a bit to the right and then a bit to the left, or else rising and lowering his face, or finally tilting his left shoulder to right and left. All these variations are seen in the face of the moon, and the large and ancient spots perceived in it make manifest and sensible what I say. And moreover, another marvel, which is that these three different variations have three different periods, for one of them changes from day to day, and thus comes to have the diurnal period. The second goes changing from month to month, and has its period monthly. The third has the annual period in which it finishes its variations. The diurnal variation is diurnal libration, already identified in the dialogue. On the other hand, the monthly pattern of changes Galileo had to tie in with the geometry of libration in latitude. That does not rule out the possibility that the observation that led him to adopt this model included the combined effects of libration in latitude and in longitude. The third declination, described by Galileo in the letter as having a yearly cycle, has nothing to do with the phenomenon of libration. Because of the end of 1637, Galileo had almost completely lost his ability to see. His studies of lunar libration did not go any further, although the phenomenon, how he described it, most likely had to have been for him an additional confirmation of his faulty theory of ocean tides, which he put forth as evidence for the movement of the Earth. To conclude, in the 30s and early 1640s, the phenomenon of lunar libration was already well known, at least among selenographers and the readers of Galileo. For example, in his book Viri Illustris Nicolai Claudi Fabrizi de Peiresque, published in 1641, Gassendi described the libration of the moon in a way very similar to Galileo's writings. However, As can be seen from works of Melan and van Langren, selenographers didn't know how to make good use of this knowledge to make lunar maps free of placement errors produced by optical libration of the moon. On the other hand, astronomers didn't create a coherent model which would account for at least the main elements of this phenomenon, stemming from the basic geometric features of the lunar orbit, although some astronomers linked libration in latitude to inclination of the lunar orbit to the ecliptic. It was Hevelius who gave first relatively complete selenographic description of lunar libration and succeeded at putting libration in the frame of a quantitative model, which then enabled him and others to make predictions that could be verified through observations. Thank you very much for your time.
Yeah, thank you very much for this interesting lecture. Are there questions? Not yet? Was it a question?
When did you why did you begin to be interested in liberation of the moon? Why?
But it is a part of a larger project concerning the science of the moon in 17th century. So you cannot speak about lunar researchers in the 17th century without understanding how they try to realize what the lunar libration is. And what is very interesting in this Hevelius treatise, De Motu Luna Libratorio, is that it was this treatise was studied by Christopher Wren, Robert Hooke, and early Newton. And as I try to show, it is quite probable that it inspired early Newton to publish his first astronomical paper in Nicolaus Mercator book. So I think it is quite important point in the history of lunar studies of the 17th century.
Can I put Suzanne's question another way? Why did Hevelius start to study libration? Tycho Brahe, if he's trying to follow in the footsteps of Tycho Brahe and in his approach to an observational program, the star catalog makes sense. But Tycho Brahe was not especially interested in what the moon looked like, as far as I know. So do we know from letters why Hevelius said, "I'm going to start to focus on the moon"?
You can read it in the preface to Selenographia. Hevelius, most likely like van Langren, would like to describe lunar phase to use lunar maps for solving problem of the longitude. So this was well, formal reason he gave, but I think this was quite smart scientific program for these times, since lunar studies were in the very beginning. So if you could devote all your time through 2 or 3 years to make good lunar maps, you can produce selenographia, and then you will become famous. So this is the second reason why I think he.
And the telescope's important. So Tycho Brahe simply could not have made the same kind of maps.
This is quite obvious observational program for young telescopic astronomy. But in Hevelius there was quite pragmatic point, the problem of longitude on the sea.
More questions? Okay, then we would like to thank for your lecture.